Hello everyone, my name is Scott Wolber. This is for EMGT 6000, the presentation modules. The topic I want to discuss today is engineers in production, specifically focusing on lean manufacturing practices. I work at an automotive OEM that supplies exhaust components to some of the biggest names in the industry, so I thought that it would be really useful to show you guys how my company performs a Kaizen event, a lean manufacturing event to improve productivity. So a Kaizen event at my organization has several main steps. You have to start with identifying the area for improvement. A lot of times production floors ship thousands of parts a day from multiple product lines. You have to zero in on a specific area for improvement to start the process. You then have to identify some goals for the improvement. These can be as simple as 30% increase in output or become even more complex than that. Third, you have to determine the products and their volumes that run through the area. This combined with number 4, perform time studies of the cell, provides the framework of the lean manufacturing event, the Kaizen event. Number 5 and 6 come pretty much hand in hand. 5, determine a machine layout that serves most of the volume. We'll talk about that word most later. And then create the standard work documentation, and this is kind of the playbook. We call it a playbook that the operators work from in the cell. It's a day-to-day operations instruction bulletin. From there, you need to fully implement, and this includes machine movement, training, posting the standard work documentation in the cell for the operators to see and use. From there, you need to record your progress to track your comparison to your goals that you set in the beginning. And then as it's Kaizen, continuous improvement, you need to repeat the process. So as mentioned from the previous slides, step 1 and 2 were identify the area for improvement and identify some goals for the improvement. Those kind of speak for themselves, so in the name of time, we're going to skip over those. Step number 3 was determine the products and their volumes that run through the area. And we do this by using what's called a PQPR, part quantity product routing. And this determines which products to help you focus on your area for improvement. It also determines what operations create those specific products. Most importantly to know here is the 80-20 rule applies. So as you can see here, 80% of my volume is made up with the first 2 part numbers, 100,070, 9005, and 9003. There's no use in me banging my head against the wall to try and fit my process to 100,248, 9099 because it only makes up 1% of my volume. So really I just need to focus on the first 2 part numbers because they make up 80% of the volume. And this 80-20 rule applies to many of the concepts in lean. It's better to make some changes that would make most of the products and processes better than to not make any changes. And with lean, it's very easy to initiate some paralysis by analysis. So one of the things we need to determine is how fast should we run the cell. This is kind of just a production pace. And to do that, we perform a takt time calculation. And takt in German actually means rhythm. So we'll take the number of hours in the day, 8 typically. So that gives us 480 total minutes per shift, minus the time for breaks, minus the time for wash up, clean up, team meetings, and anything else that happens to occur during the shift. That gives us 415 total minutes available per shift. So 415 minutes, 24,900 total seconds per shift, divided by the number of pieces that we need to fulfill a yearly demand. So this will be 415 times 250 shifts per year. That's our total annual demand, which means we need to produce a part every 60 seconds. So that's our goal, is to create a part every 16 seconds so that we are creating some just-in-time manufacturing. So now you're going to perform step number 4, which is create time studies of the process. So on the left, we've broken out the tasks required to create a full assembly. You're actually going to shadow the operator as they perform these tasks for a number of cycles. And a cycle is defined as the total processes that are required to create a full assembly. So in this example, we're shadowing the operator for 10 cycles. You're actually going to record a flowing time as the operator just does everything that's required to build this assembly. So for example, Cycle number 1, load and unload first machine cycle start took 7 seconds. Step number 2, walk to lathe took 2 seconds. And if we zoom over to cycle number 6, walk to the assembly bench, that took 3 seconds. Then the operator took a break, so we start the time over after that on cycle 7. Now if we zero in on cycle number 8, step number 3, you can see that there was an abnormality. 87 seconds just doesn't fit into the mold, so something happened there. Generally, we'll take some notes and record any abnormalities such as that. And on the right, on the far right, we'll take the lowest cycle time that was recorded in each column. So we add those up at the bottom, we sum up 31. So in a perfect world, this cell can create a part every 31 seconds because there's 31 seconds of total work in the cell. After we create the time studies, we need to create a machine layout, and this is probably the most difficult step, at least for me. So what my company does is we create the virtual space with scale models. So on the right here, this grid is actually 6 inches by 6 inches, and then we will use shapes, and actually this is just Excel. We'll create shapes in Excel that are scale models. So this will allow us to kind of twist our machinery around and place it in places without actually moving it and trying it in real life, because a lot of this machinery weighs several tons. So some of the characteristics of these cells that we try to create, they're U-shaped, they flow counterclockwise, that is, the operators will actually walk counterclockwise. So most of the time this is just because most operators are right-handed, so as they walk around the cell, the machine is on their right side, so they don't have to twist as they perform the operation, so it's a little more ergonomic. Raw goods come in exactly when they are needed. So in the top right of this example here, you can see a flow rack, and this flow rack is actually bringing, I think it is like an end cap or some other raw good, precisely at the time that it's needed and not before that. This eliminates some excess carrying. And then all machines are in a straight line. This prevents any tripping and also makes the cell look neat and tidy. From there, you can create your workflow documentation, and we do this with 3 main documents: the standard work operator loading chart, the standard work combination sheet, and the standard work cell layout sheet. So the standard work operator loading chart just basically shows the layout of how the operations are spread among the 3 operators that we have included in the cell. And in this example, the takt time was 40 seconds. So you can see that every operator is well below the 40 seconds and they should be able to meet the production requirements. The standard work combination sheet is actually kind of each operator's playbook. It tells them which operation to do and when, and then gives them a target time. And all this will actually be posted in the cell for the operators to check up on. Finally, the standard work cell layout sheet actually provides pretty much a roadmap and allows the operators to see how they're going to flow throughout the cell doing their work. Now it's time for the really fun part, implementation. This requires you to move machinery, move electrical, air and other machine requirements. Whatever the machine needs to run, you're going to have to move those supply lines. You need to train the operators using the standard work documentation that you created previously, and also train the supervisors so that they know how the cell is supposed to be run. As you can see on the right here, this is one of our production cells in my facility. All the machines are in straight lines. It's U-shaped. On the right there, this basket, these are the raw materials that are coming in, and then directly out of the picture on the lower left-hand side is actually where the finished goods come out. So goods in, goods out in the same location. It allows for easy loading of the cell and allows the material handlers to get the material in and out of the cell. Now for one of the hardest things in the lean implementation process, actually recording your progress. So we tend to use these hourly status boards as seen on the right. With these, our progress is recorded every hour. The goal includes breaks, lunches, etc. And this also allows for instantaneous determination of problems. So the goal lists pieces per hour that's required, or what we're shooting for. And on the right there is the cumulative total. So in hour 8, we're aiming to make 62 parts, and the daily total would be 668. And then on the right hand side, you can see the takt time is 40 seconds. And if there is a miss for the production goal, they need to list the reasons for that. It could be man, machine, or material requirements. Either one of any of those 3 could drive a miss for the goal. So what you're actually seeing here is a screenshot from our software that we use to track our lean manufacturing events. And the most important number, well, the one that management seems to care the most about, was the number on the right, the annual savings from the 2-day event. This 2-day event involved 4 people, so 64 total man hours, assuming 8 hours per day per man, resulted in an annual savings of $40,000. So this lean manufacturing stuff is the real deal, and it's really well worth the time investment. So that concludes my presentation on the lean manufacturing practices. Thank you for listening today, and I look forward to all your questions on the discussion board. Thanks. Bye.